Welcome back. In this class, we'll be learning about three-phase synchronous generator. We also call it as alternator. So this three-phase synchronous generator generates three-phase AC voltage, and the speed at which the rotor is rotated is at a constant speed, so that the AC voltage that is produced has a constant frequency. We also call this as alternator as it generates alternating voltage. What is a generator? Electrical generator is basically a machine which converts mechanical energy into electrical energy. This alternator is used in the power industry, in thermal power plant, in hydro power plant, and also in nuclear and diesel generation. Now, as I said, it will work at a constant speed so that the frequency of the generated EMF is constant. If the speed is not constant, then the generated EMF will have different frequency, which is not desired. The speed at which it rotates, we call that as synchronous speed, and that's the reason we call it as synchronous generator. From the basic law of electromagnetic induction, we know if there is a relative motion between the flux and the conductor, then there will be an EMF induced in the conductors. Now, important point is relative motion. Now, when we have a stationary conductor and the magnetic field is rotating, then we will have induced EMF. At the same time, if we have the magnetic field is stationary, but the conductor is rotating, even then we'll have a EMF induced. In case of alternator, we keep the conductor stationary and the magnetic field is rotated. The basic concept is we will have the conductors which are placed in the stationary part of the machine, and we have the magnetic field which will be rotating. Now, to obtain this magnetic field, we do not use any permanent magnet which provides a magnetic field. Instead, we use a field coil which is placed in the rotating part. In the field coil, a DC supply is given. So when the current flows in the field coil, it produces a magnetic field. And once that magnetic field is produced, it acts as a magnet. Now, this rotor is rotated by using a prime mover. So as the rotor is rotated, field coil placed in the rotor will rotate. That makes the magnetic field rotating. So when the magnetic field is rotating and the armature conductor is stationary, but there is a relative motion between this armature conductor and this rotating magnetic field, so we will have EMF induced in the stationary armature conductors. This is the basic working principle of synchronous generator. So this is a cut section of a synchronous generator. We will see this construction in details. So when we talk about construction of three-phase alternator, we can understand from the previous discussion that we will have a stator and we'll have a rotor. In the stator, we will have the armature conductors which are placed, and in the rotor, we'll have a field winding placed. And in the rotor part, that is in the field winding, should have a supply, DC supply, through which the field winding will act as a magnet. So from this diagram, we can see that this outer periphery, you have this part that is called as the stator. Inside the inner periphery of this stator, we will have a slots made. These are the slots. These are the slots. In these slots, the stator armature conductors are placed. So this is called as the stator winding, where we are placing this armature conductor. This outer frame, we call it a stator frame or core. This is the field winding. This is the field winding. This is the pole. This part we call it as pole core, and this part we call it as pole face or pole shoe. This field winding is placed such that alternate north and south poles are created. So as we know, depending on the direction of the winding, this will act as a north pole or south pole. So this uses right hand thumb rule. So when we use our right hand, pointing out thumb towards outside, then if the direction of the fingers points towards the direction of the current flow, then there will be a magnetic field produced in the direction of the thumb. So that says that if current is flowing in the direction of other four fingers, then this will act as a north pole, as from north pole the magnetic field is pointing towards outer direction. So this will act as north pole. In that case, in the second pole, the winding should be placed in such a way that it will point towards the pole so that it will act as south pole. That is how it is made sure that if this is north pole, this will be south pole, and the next one is again north pole, next one is again south pole. We can have a machine with multiple number of poles. The picture shows a 4-pole machine. We can have a 2-pole machine, 4-pole, 6-pole, 8-pole, or more. This is the base on which this whole machine stands. So this is your basic construction part. So we have one stator which is placed on the outside, and inside that we have this rotor. This rotor can be of two types. One we call it a salient pole rotor, another one we call it as non-salient pole rotor. So this is the stator part. Here we have the armature windings placed where the EMF will actually be induced. So from this outer periphery, we'll be taking out the terminals through which we will be collecting the induced EMF. And inside this, we have the rotor, which will be inserted inside this, so that this rotor can rotate freely inside this stator. Now, here we have the field winding placed. Here we have the field winding placed. What we do, through a slip ring, there will be a connection so that DC supply can be given to this field winding. As DC supply is given to this field winding, there will be a magnetic field generated. Now, using this spindle, it will be connected to a prime mover, and through that prime mover, this rotor will be rotated. So there is a magnetic field produced, and the magnetic field is made to rotate. So the stationary conductors will have an induced EMF. And that induced EMF can be collected easily from the stationary armature. So this is the basic part, basic working part and the construction part. Now let's see in detail. So now what do we have in the stator? Stator is basically the stationary part of the machine. It is built up of silicon steel laminations having slots on its inner periphery. Why do we have these laminations? We have these laminations because this laminations will reduce the eddy current loss. If we do not have these laminations, if it is a solid core, then eddy current loss will be more. So this laminations reduces eddy current loss. And we use the material silicon steel. We use the material silicon steel so that we can have reduced hysteresis loss. Silicon steel reduces hysteresis loss. And in the inner periphery of the stator, we'll have the slots. And in these slots, because we have these slots placed in the inner periphery of the stator, in these slots, we can place the armature conductors, and armature conductors, which are placed in multiple slots, will be connected together to form a three-phase windings. Three-phase windings means there will be three phases, and it's connected such that there is a 120-degree phase displacement between all these three windings, so that three-phase AC can be generated. The armature winding is always connected in star, and the neutral is connected to ground. For all alternator, armature winding is always connected in star, and the neutral point is grounded. So this is the stator. So here we can see this outer frame, which is the stator frame. Inner periphery, we have the slots made, and inside the slots we have the armature conductors placed, and armature conductors are connected together to form a three-phase star connected winding, and the whole thing is placed on a base. This part is required so that it can be placed on the ground or a tabletop or whatever it is. And this outer frame is made up of silicon steel but laminated one. Lamination reduces the eddy current loss, and silicon steel is used to reduce the hysteresis loss. And this base is made of cast iron so that it can provide enough strength. So this is about the stator. Now coming to the rotor, as we know, we can have two types of rotor in case of synchronous generators. So one can be salient pole rotor, the other one can be non-salient pole rotor or cylindrical rotor. So in the salient pole rotor, it looks like this. You have a core and the poles are projected outside. So projecting poles are mounted on a large circular steel frame. So this is made up of a steel. This is a steel frame. On that, the poles are mounted and it is projected outward. So this is showing a 4-pole machine. We can have 6-pole or 8-pole machine as well. Now, when we use the salient pole machine, and as you know, the field winding has to be placed here. So this is the field winding which are placed. We can see here clearly that in this case, this is the direction of the current. So using again right hand thumb rule, we can understand that this will be acting as a north pole. Here, the direction is opposite. Direction of current is opposite. So this will give us south pole. Using the right hand thumb rule, again we can understand that it will give us south pole. So direction of magnetic field is inward. That indicates this will be south pole. Here direction of magnetic field is outward. So that will indicate it is north pole. So alternate north pole and south poles are created through this connection of field winding, and in the field DC supply is given. Now when we use the salient pole machines, we can see that air gap is not uniform. This is the pole face and this is the pole core. Here the distance is less, whereas here the distance is more. This part shows that the air gap is not uniform in case of salient pole machines. And when the air gap is not uniform, we can also say this is projected outside. So this will have less mechanical stability. So because it has a less mechanical stability, the speed of the alternators, that salient pole alternator, cannot have a very high speed. We can have speed up to 500 RPM and not more than that. This is used in diesel engine or water turbines, and large diameters and short axial length is used. This one will have a large diameter and axial length will be less, short. And since this has less mechanical stability, to increase the mechanical stability, we can have more number of poles. If the number of poles are increased, then the uniformity in air gap can be obtained. So we can reduce the non-uniformity by increasing the number of poles, and also the mechanical stability can be increased by increasing the number of poles. So salient pole rotor will have low speed, it will have higher number of poles, it has less mechanical strength, it has large diameter and short axial length. Coming to non-salient pole or cylindrical rotor, it's like this. You have North Pole, South Pole, North Pole, South Pole. So this is shown as 4 poles. In the outer periphery, we have the slots made. In the outer periphery of this non-salient pole, we have the slots made, and in the slots, the the conductors, field conductors are placed. Field windings are embedded in these slots basically. It's a cylindrical shape. It has the conductors placed like this, and through these conductors they are connected, and that gives us the field winding. Here we can see that air gap is uniform. Because it is cylindrical, in the outer part of this, here we'll have the stator frame, where we again have the armature conductors placed. So in between this rotor and the stator, the air gap remains uniform throughout. Whereas in this case, in the outer periphery, after this, we have the stator frame. So from here to here, the air gap is more, and from here to here, the air gap is less. So air gap was non-uniform in case of salient pole rotor. In this case, after this, if I have the stator frame, air gap is mostly uniform throughout this periphery. This has higher mechanical stability, so it can have higher speed. These alternators can go up to 1500 to 3000 RPM. This is used in steam turbines. And the number of poles in cylindrical rotors are comparatively less with respect to the salient pole rotor. We will see later, as the number of poles are increased, the speed is reduced to have the same frequency. Now, as we have already explained, but again, let's recap about what is the working principle of alternator or synchronous generator. In synchronous generator or alternator, armature winding is stationary. Field winding is placed in the rotor and it is excited by a DC supply. Current in the field winding produces the magnetic field. As the DC supply is given, there is a current flow in this field winding, and that produces the magnetic field. We do not use any permanent magnet, it's an electromagnet. When the DC supply is present, it acts as a magnet. If DC supply is not given, it does not act as a magnet. So this DC supply produces the magnetic field. Now rotor will be rotated by using a prime mover. So as the rotor rotates, rotating magnetic field will be produced. The magnetic field is already produced. Now the magnetic field is rotated. When rotating magnetic field cuts the stationary armature conductor placed in the stator, it will produce the EMF. So as there is a relative speed between stationary armature conductor and the rotating magnetic field, there will be an induced EMF in the three-phase winding which is placed in the stator. And from this three-phase winding, the output is taken. Now, how do we connect this DC supply to the field? Because the rotor is rotating, to connect the DC supply, we need to use something called slip ring, so that the terminal which is connected from the DC supply remains stationary, whereas this stationary terminals supply positive and negative voltage to two terminals of the field winding which is rotating. So it basically it transfers from a stationary terminal's polarity to a rotating terminal. So that is called as slip ring. So this is the basic working principle of alternator. Now, how do we calculate the EMF of this induced EMF? In turn, this will give us the speed at which the rotor should rotate, and the frequency of induced EMF can be calculated from this concept. Now, we understand this, that is, we have an N pole, we have an S pole, so this is the magnetic field which is produced. So in between this, we have the magnetic field lines. If we place a conductor, here, then if this conductor is rotated, so there is a magnetic field which is stationary, we have a conductor which is rotated, then there will be induced EMF across these conductor terminals. So from here, we can see that from these two terminals, we'll be taking this output voltage, and which is supposed to be AC. So why it is supposed to be AC? Because this induced EMF follows the concept of electromagnetic induction, which is given by minus n d phi dt, and when we calculate, we get it as VLV sine theta. So V is the flux density, L is the length of the conductor, and V is the velocity at which the conductor is being rotated. So if we have VLV known, then we can find out that the induced EMF is proportional to sine theta. Now, from here we can understand it further. This we have already discussed while discussing single phase AC generation as well. So we have the conductor position like this. This is the magnetic field. Remember one point here. When the coil is placed at an angle of 90 degree, maximum flux is getting cut, but induced EMF is minus n d phi dt. So minus n into rate of change of flux, so which will remain minimum, and the induced EMF is 0. When this is in the line with the flux, then we get rate of change of flux as maximum, and then we get the maximum EMF induced here. Sine theta, VLV sine theta. So when the theta is 0 degree, we get induced EMF as 0. When theta is 90 degree, we get induced EMF as maximum. Again at 180 degree, we get it 0. Again at 270 degree, we get it negative maximum. This is how we get the induced EMF generated. So this is for a single phase AC generation, the basic principle of single phase AC generation. Now coming to this alternator, we have, let's see this, we have one N pole here, one S pole here, one N pole here, one S pole here. Now this full sinusoid that I am getting here is from one N pole to S pole and back to the N pole. From North Pole to South Pole, when the conductor rotates by 180 degree, when the conductor rotates by 180 degree, this side of the conductor moves from North Pole to South Pole. Another 180 degree means the same conductor comes back to the North Pole. So one full cycle of 360 degree is obtained from North Pole to South Pole back to North Pole. If I have, this is in case we have 2 poles in the system. If I take 4 poles in the system, then from North Pole to S pole, when the conductor moves, in alternator, conductor does not move, the rotor itself moves. That means the poles are moving. So if I take this conductor, this North Pole is aligned with this conductor. Now when this North Pole goes here, that means this South Pole comes here. So from this North Pole to this South Pole, suppose this is rotating in clockwise direction. So this N pole goes here. That means this South Pole comes here. So with respect to this conductor, there is actually a mechanical movement of 90 degree, but it has shifted from North Pole to South Pole. So the induced EMF's angle will be 0 degree to 180 degree. Though the mechanical angle is 90 degree here, but the electrical angle is 180 degree. Again, if it rotates further, this N pole had come here, S pole had come here. Now that S pole will go here and this N pole will come back here. And that will give one more 180-degree rotation. So a complete 360-degree rotation of electrical cycle can be obtained from one north to south to the next north. Similarly, when I get that north to south to north, another 360-degree rotation we will obtain. So for a 4-pole system, I get this complete cycle of electrical AC generation of 2 full cycle. For a 4-pole system, for one complete mechanical rotation, I get 2 complete cycle of electricity generated. If it is a 6-pole system, then from N to S to N, that gives us 1 full cycle. So we'll get 3 full cycles of electricity generated in case of a 6-pole system. Right? So from this we understand that one mechanical rotation of rotor is equal to P by 2 cycle of EMF electrically. When I have only 2 poles, then I have only 1 cycle. When I have 4 poles, I get 2 cycles. If I have 6 poles, I get 3 cycles. So I can say that one mechanical rotation of rotor gives P by 2 cycle of EMF electrically. So if I consider the rotor is rotated at a speed n RPM, that means n rotations per minute. So we need to find out the frequency. Now what is frequency? Frequency is cycles per second. So if number of rotation per minute is n, number of rotation per second can be n by 60. To calculate the frequency, which is cycles per second, I can find out cycles per rotation. Here we have got one mechanical rotation, that means one rotation. How many cycles did we get? P by 2 cycles. So cycles per rotation is P by 2. And number of rotation per second is n by 60. So what is the cycles per second? Cycles per second is P by 2 multiplied by n by 60. And that is nothing but cycles per second. So it's nothing but frequency. So frequency is P into n by 60 into 2. So Pn by 120 is nothing but the frequency of the induced EMF. So if the rotor is rotated at a speed n RPM and we have P number of poles, then we'll get the induced EMF frequency as Pn by 120. What is called as synchronous speed? Synchronous speed is to obtain a constant frequency, we need to rotate the rotor at a constant speed. So for a given machine, number of poles remains constant. So if I rotate at a constant speed, I'll get a constant frequency. So for a specific frequency, I will get a specific speed at which the machine has to be run. So that gives us the synchronous speed. So if I say that I have a 2-pole system and I need the frequency as 50 Hertz, which is standard in Indian system. So for a 50 Hertz frequency, for 2-pole system, synchronous speed can be calculated as 120 into 50 by 2, so which is 3000 RPM. That gives that for 50 Hertz system, we cannot have a synchronous machine which runs more than 3000 RPM because we can never have number of poles less than 2. To obtain higher synchronous speed, number of poles should be reduced. So if frequency remains constant at 50 Hertz, we cannot have a synchronous machine which runs at a speed more than 3000 RPM. So if the number of poles is 4, then synchronous speed is 1500. If it is 6, it is 3000, 8, 750, and so on. So we can say that when I need higher speed, the number of poles should be reduced. That is the reason when we talk about non-salient pole rotor, I can run it at a higher speed. I can run the non-salient pole at a higher speed because it has a better mechanical stability. So to run at a higher speed, number of poles should be less. Whereas for salient pole machines, it has the less mechanical stability. So we can run it at a lower speed. We cannot run this motor at a higher speed. So salient pole motors will have more number of poles to obtain less speed. We have already understood the relationship between mechanical angle and electrical angle. We have seen here in two-pole machines, when we get a complete rotation, that means a complete mechanical rotation, I get a single cycle. For four-pole system, when I get a complete rotation, I get two complete cycles. When I have a six-pole, then I get three complete cycles. So from here I can say one mechanical rotation, which is 360 degree, and electrical rotation is also 360 degree. For four-pole machines, one mechanical rotation, that is 360 degree, gives us 720 degree electrical rotation. So from this relationship, we can obtain mechanical angle is equal to number of poles divided by 2 into theta electrical. So this is theta mechanical, that is mechanical angle, is equal to number of poles, that is P, divided by 2 multiplied by theta electrical. Now, as we are talking about armature winding, we need to have a basic idea about some winding terminologies. Now, what is a conductor? Conductor is the conductor which we are placing in each slot. And that conductor has to be connected to another conductor to finally form the winding. Now, one conductor placed in one slot, another conductor is placed in another slot. It is not in the adjacent slot. It is usually at a distant slot. We'll see how far it is in a short while. So now from one conductor which is placed in one slot is connected with another conductor which is placed in another slot. This complete thing is called as a turn. From here to here, this is called as a turn. And the conductor which is placed here is the conductor. So we can say that two conductors makes a turn. Two conductors make a turn. In one slot, it's not necessary that only one conductor has to be placed. There are multiple conductors which are placed in a slot and they are connected to the conductors which are placed in another slot. The whole thing is called as coil. One single conductor here and another single conductor here, when they are connected together, that is a turn. When multiple conductors here and multiple conductors here, they are connected one to other. This whole thing is called as a coil. And in one slot, this bunch is called a coil side. This is a coil side. This is one more coil side. They are connected to form a coil. So here there is one conductor placed. Here there is one more conductor placed. Two conductors are connected to obtain a turn. Like this, multiple turns together are called as a coil, that is multi-turn coil basically. In one slot, a part of the coil, that is called as coil side. Now, this is the slot, these are the slots. This whole thing is the rotor's slots. This is shown as if it is a cylindrical rotor. So in the outer periphery, we have the slots made. Here there is a coil side. Here there is one more coil side. So from this coil side, it's connected to this coil side. So from one pole here to next pole, what is the distance from one pole to the next pole? It is this red point to this red point. This distance is called as pole pitch, and it is expressed in terms of number of slots per pole. So how many slots do we have here in the overall outer periphery? If it is say 16 and we have 4 pole, then from one pole to another pole, I have 16 by 4. So 4 slots per pole. So total number of slots divided by number of poles gives us slots per pole, and that is how pole pitch is expressed. Pole pitch is nothing but distance between one pole to another pole, and that is expressed as number of slots per pole. So total number of slots divided by number of poles. What is a slot angle? Slot angle is what is the electrical angle made by two adjacent slots. So from this slot to this slot, what is the angle? That angle expressed as electrical angle is called as slot angle. So as we know, from one pole to next pole, the electrical angle is 180 degree, whatever be the number of poles. From one pole to another pole, the electrical angle is always 180 degree. If it is a 4-pole system, mechanical angle is 90 degree. If it is a 2-pole system, mechanical angle will be 180 degree. If it is a 6-pole system, mechanical angle will be one pole to another pole, mechanical angle will be 360 by 3, 120 degree. But electrical angle from one pole to another pole is always 180 degree. So I can calculate slot angle is equal to alpha, which can be written as 180 divided by small n. Small n is what? Small n is slots per pole. So from here to here, how many slots do we have? Those many slots will make an angle of 180 degree. So 2 slots in between them, what will be the angle? That's nothing but 180 by slots per pole. So that's called as slot angle. Now, few more terms: concentrated and distributed winding. What do we mean by this? This is basically if the winding, armature winding or the field winding, whatever we talk about, whether the winding is placed in one slot or it is distributed in all the slots. It's always distributed in all the slots, right? So when we talk about the armature winding, in the inner periphery of the stator, we have multiple slots made, and in all the slots there are few conductors which are placed, and they are all connected together to form the 3-phase star connected winding. So the winding is distributed in the whole periphery. So we call that as distributed winding. If whole winding is placed in one place, then we will call that as concentrated winding. So at this point, we need to understand that in case of alternator, we do not use concentrated winding and we use distributed winding. And because of this distributed winding, the EMF induced will be reduced. How? What is the factor? We'll calculate it in a while. Another term is single layer and double layer winding. In one slot, if we have a single coil side, then we call that as single layer winding. If we make it in 2 layers and 2 sets of coils we can place here, then we call that as double layer winding. It looks like this. Here we have shown here. See here, 2 sets of coils are placed here. So this is double layer winding. So usually we use double layer winding in case of alternator. Okay. Now going to the next, full pitch and short pitch coil. Here we need to understand, as I said before, that if one coil side is placed here, the next coil side with which this coil side is connected is placed here. So it's placed at a distance. Now, what is the distance? That distance is measured by this. That's what we call it as pitch. So if from one slot to one slot, whatever conductors you are placing are connected to this slot's conductors, if the distance between this slot and this slot is 180 electrical degree, we call that as full pitch coil. So this is full pitch coil. So I repeat, the conductors which are connected, which are placed here, if they are connected with the conductors which are placed in this slot, if the distance between these two slots is 180 electrical degree, we call that as full pitch coil. We call that as full pitch coil. If the distance between this coil side and this coil side is less than 180 degree, then we call that as short pitch coil. We call that as short pitch coil. So when we have this distance 180 degree, what does that mean? That means if a coil side is placed here, with that, which coil side will be connected is here. So from this pole to this pole. So if it is not here, if it is here, then this will be here. If it is here, then it will be here, like that. So distance between one coil side to the coil side with which it is connected, if the distance is one pole pitch, then we call that as full pitch coil. Because when it is a distance of one pole pitch, the angle will be 180 electrical degree. If it is short by one slot or two slots, then we'll call that as short pitch coil. Now the term comes, if it is short pitch, the induced EMF will be slightly reduced. So coil span factor or pitch factor is the ratio of voltage generated voltage in short pitch coil to the voltage generated in full pitch coil. So if the coil is a full pitch coil, generated voltage will be higher. If the coil is short pitch coil, then the generated voltage will be lower. This factor by which the induced voltage gets lowered, that factor is called as coil span factor or pitch factor, and it is calculated as Kp, which is coil span factor or pitch factor, is equal to cos K alpha by 2. What is alpha? Alpha is the slot angle. This is the alpha, which is 180 by n. N is slots per pole. This is alpha. So we calculate it as cos K alpha by 2. What is K? Number of slots by which the coil is short pitched. So if it is short pitched by one coil, then it will be cos 1 into alpha by 2. If it is short pitched by two slots, then it will be 2 into alpha by 2. So that is pitch factor. What is distribution factor? Distribution factor is the factor by which induced EMF is reduced due to distribution of coil. That means because the winding is distributed. So what is the factor by which induced EMF is reduced by? That is called as distribution factor. And this is calculated as sine Q alpha by 2 divided by Q sine alpha by 2. So sine Q, what is Q? Q is slots per pole per phase. We are talking about a 3-phase generators. So number of phase is always 3. So what is the number of slots divided by number of poles divided by 3 is Q. So if it is a 36 slot system and number of pole is 4, then it will be 36 divided by 4 divided by 3. So 36 by 4, that is 9, divided by 3, that is 3. So Q will be equal to 3 for a 36 slots 4 pole system. So that is KD or distribution factor. How do we calculate winding factor? Winding factor is nothing but Kw is given as Kp into Kd. So this Kd and this Kp, this will get multiplied to obtain this Kw. Now the final one, that is EMF equation of alternator. How do we calculate this EMF equation? How do we derive this EMF equation? Basically, we can say that there are, say, p number of poles, and phi is the flux per pole. That is, the flux produced by each pole is phi. Then if I take one conductor which is placed in stator, what is the total flux that this conductor will cut in one complete rotation? Because the conductor will come in contact with all the poles. So the total flux cut by each conductor during one revolution is P into phi Weber. And time taken for one complete cycle is 60 by n second, because n RPM, n rotations per minute. So for one rotation, the time is 60 by n second. How do we calculate the average EMF induced per conductor? Total flux divided by total time. So for one rotation, this is the total flux and this is the time. So flux by time, that is P phi n by 60. This is the average EMF induced per conductor. This is per conductor. If I want to calculate average EMF induced per phase, how do I get this per phase? If I consider that ZPH is the number of, this is the number of conductors per phase, then I can write whatever average induced EMF we have got for one conductor multiplied by Z phase will give us the average EMF induced per phase. Now this can be written as P phi n by 60 into Z phase I have written. This is conductor per phase. Now as we know, two conductors make one turn. So Z phase means it is 2 into T phase, where T phase is number of turns per phase. Because two conductors makes a turn, so Z phase is equal to 2 T phase. Then what is the average induced EMF? This is the average induced EMF. Now just simplifying this, just writing this again so that I can write in terms of frequency, and we have frequency which is Pn by 120. F is equal to Pn by 120. We have derived here. F is equal to Pn by 120. F is equal to Pn by 120. We have derived here. So we are just writing in terms of that. So here we are taking this Pn by 120. So it was 60, we have written it as 120, so multiplied by 2. So numerator also should be multiplied by 2. So I can write it as 4 TPH into 5, 4 into 5 into TPH into Pn by 120. So 4 5 TPH multiplied by Pn by 120, which is nothing but F. So 4 5 F TPH is the average EMF. Because we are talking about generated AC, AC is expressed in terms of RMS value. So instead of expressing in average value, we need to express in RMS value. From the definition of form factor, we know that RMS value of induced EMF per phase is equal to average value per phase multiplied by form factor, because form factor is RMS value by average value. So from that we get EMF induced per phase, the RMS value of it is equal to 4 5 TPH, which we have calculated here, multiplied by 1.11, because 1.11 is the form factor for a sinusoidal AC. So we get it as 4.44 5 FTPH volts. This is E phase. Now this is E phase, considering that is the induced EMF, considering that it is full pitch coil and it is a concentrated winding. But in practice, it is not concentrated winding, or nor it is a full pitch coil. It is practically distributed and short pitched. So if I take that coil span factor is Kc, that is pitch factor is Kc, or you can write it as Kp as well, and the distribution factor is Kd. Kc is nothing but Kp. then we can write this EMF induced as whatever we had multiplied by Kc into Kd or Kp into Kd. Kc is nothing but Kc is equal to Kp. So induced EMF is equal to 4.44 Kc Kd phi f into Tph volts. So this is the induced EMF expression. Thank you.